In Chapter 7, we're going to move beyond the particle model, right? So far in this class, everything we've done has been using the particle model. So whether we were talking about a basketball player or a mountain goat or a spaceship, we treated everything as a little dot, right? All forces came off of that dot. We didn't ever talk about the spatial extent of anything. Dots can't rotate. How could you tell if a dot rotated, right? So that's all the particle model. Everything so far has been in the particle model. Well, obviously, not everything is a particle, right? A dot is not a super good representation for every possible object in the universe, right? So in this section, in Chapter 7, we're going to dig in and we're going to go beyond the particle model. And we're going to start by talking about rotations. So, everything we've talked about so far it's been a straight line, right? So in other words, we've never talked about objects rotating, like I said, right? We've always talked about just objects going somewhere. They can have a curved path, right? Or go in a circle, right? But that's different from the object itself rotating, right? The object itself moving in a circular path is different from the object itself rotating. And so that's what we're going to add in this chapter. And so we've talked, like I said, a lot about objects going somewhere. We call that translational motion. Now, in general, an object's motion will combine both some rotation and some translational motion. So here I have this spaceship, and if I move this spaceship from here to here, then that is translational motion. Purely translational motion. The orientation did not change. However, in general, the motion of the spaceship will not be purely translational, right? If I give it a little toss, you can see it is rotating and going somewhere. Woo! Okay, it's kind of fun. I guess I know why my kid likes that one so much. Okay, so in general, motion is both rotational and translational. And the nice thing is, like a lot of things in physics, our strategy is to break those apart. The nice thing is we can deal with them separately, right? So we've got this rocket ship and it's doing that, right? In order to analyze that motion, we could treat it in the particle model as an object in projectile motion and then just add in the rotation to it. And that's what we're going to talk about here today, is the rotation part of that. So again, translational motion, that's going somewhere. Rotational motion, that's self-descriptive, that's rotating motion. Okay, in order to do this, we need a new quantity, and that is angular acceleration, right? And so, if I've got some object and its rate of rotation changes, then it has just undergone some angular acceleration, right? So here we have a bicycle tire. Right now, its angular velocity is 0, right? If I put my hand on it and I apply a little force here, then I can cause it to start rotating. So its angular velocity was 0. Now it isn't. It underwent some angular acceleration, didn't it? And now if I put my fingers here and I bring the bicycle wheel to a stop, it is accelerating. Angular acceleration, because it is its rate of rotation that is changing, right? Now, much like we defined acceleration, just regular old acceleration, as a change in velocity, so too we will define angular acceleration as a change in angular velocity. So a change in angular velocity over some time interval is an angular acceleration. And we use this little fishy guy here. This is alpha. That's Greek letter alpha, the first letter in the Greek alphabet. And so here, we could do a motion diagram for some dot along the rim here. And we can see that since these dots are getting farther apart, that this wheel its rate of rotation is increasing. Therefore, it is undergoing some angular acceleration. Here we in this figure we see here an omega initial, which is smaller than this omega final. So clearly, omega is changing in time. Therefore, there is some angular acceleration. And I'll just remind you that this letter here is omega, and that omega is the symbol we use for angular velocity. Recall that angular velocity is a change in angle over change in time. Well, we could measure this angle in degrees or even rotations. Our standard SI way of dealing with this would be to use radians, right? And so you'll never get in trouble here using radians per second. You might get in trouble using degrees per second or rotations per second or RPMs, rotations per minute. You just have to be more careful if using those non-standard units. Okay, so that's angular acceleration. It's not too bad, right? It just says, hey, the rate of rotation is changing. It is a little bit tricky. It is a vector. The nice thing is in this class, we don't get into a lot of the details on the vector nature of these rotations. And we're not going to do a whole bunch of kinematics problems with rotations. So we're going to talk about rotational motion. But really, we're not going to get too in-depth with it. So talking more about alpha here, it is a vector, like I just said. And so it can either be positive or negative. In the case of angular acceleration, we use a sort of simplified coordinate system where we define things in terms of clockwise and counterclockwise. So our standard issue here is that a counterclockwise rotation is positive. And that's a little bit surprising, I guess, but you've seen this convention before most likely, right? If we drew a standard XY coordinate system, and we had some vector here. Sort of our default, and we've seen this in homework problems, right? Our default, if nothing else is specified, is that we're going to measure our angle above the x-axis. To be more specific, we're going to measure it counterclockwise from the x-axis. And so this is the convention we'll adopt, where counterclockwise is positive and clockwise is negative. Okay, and that's just a convention. It could be the other way around, but it's not, right? This is not something that's based in logic. It's based in something just we have to decide so we can all be on the same page. Okay, when in doubt, call counterclockwise positive. Okay, and then much like with straight line acceleration, we can have positive accelerations or negative accelerations, and we have to be super careful because a positive acceleration does not necessarily mean speeding up, and a negative acceleration does not necessarily mean slowing down, right? And so here we see that an object is, if it is speeding up in the positive direction, then that is a positive alpha, or slowing down in the negative direction, also a positive angular acceleration. Alpha is negative if we see something that is slowing down while rotating in the positive direction, or speeding up while rotating in the negative direction, right? So it's similar rules there to straight line acceleration. We have the same exact rules for straight line acceleration, right? Velocity and acceleration, that object is slowing down because they're in opposite directions. Velocity, acceleration, that object is speeding up because they're in the same direction. If we're talking about straight line, or sort of our standard acceleration that we learned about in Chapter 2, velocity and acceleration, what's that object doing? If they're at right angles, that object is turning a corner. That's a little bit different than angular acceleration. So centripetal acceleration is different from angular acceleration, and I'll review that idea here in just a second. It's nice because we've dealt with a lot of this logic already, right? Like I said, I just went over those rules for acceleration real quick. Why? Because we've already learned them. They're the same rules we learned for just regular acceleration measured in meters per second squared. I should say that angular acceleration, its standard units, are radians per second squared, right? Because I'd said that the standard units for omega is radians per second, right? And if we divide radians per second by seconds, then this would be radians per second squared. So that's our standard unit for angular acceleration. So anyway, we've built up this logic for thinking about the straight line motion, and the nice thing is we can use that same logic and apply it to circular motion, right? And so if you can rely on this analogy, then there's a lot fewer new ideas in this chapter if we can build up this analogy with linear motion. So in linear motion, we use x to represent position. We might measure it in meters or feet or something. In circular motion, we use theta to measure our position. And so this could just be, like 30 degrees or 90 degrees, the way we normally think of an angle, but it could also be like, 360 degrees or 2 pi radians. Well, that's all the way around, but it could be 720 degrees or 4 pi radians, right? That would be twice around. Heck, it could be 1468 pi radians, right? That's many rotations. So, again, you know, this isn't just one fixed position. Things could go around and around and around, possibly. For linear velocity, it's a change in position over change in time. Well, angular velocity is the same, a change in angular position over change in time. Acceleration is a change in velocity over change in time, and angular acceleration is just a change in angular velocity over change in time. Again, the logic you've built up and learned in the first 6 chapters of this book, it works here too. We just have to extend our thinking a tiny bit. Okay, so we talked about why we defined radians, right? We talked about that in a previous lecture. And the nice thing about using radians to measure angles, right, is that if we get this pi shape here, then we have this really nice relationship, right? That the length of this arc is equal to theta times r, as long as we promise to measure theta in radians, right? And so again, as discussed in a previous lecture, this is why we use radians. This is why radians are useful to us. So this is our basic equation. If those of you that have had calculus, if we take a derivative of this equation, we end up with this equation, a derivative with respect to time. Notice that r is not changing, right? And anything that doesn't change with time gets left alone when we take a derivative. Again, if you haven't had calculus, it's no big deal. If you have had calculus, then you can probably see the math that leads from here to here. And then again, we take another derivative of both sides to get to here. You don't need to know that calculus to understand how to use these equations. I guess the real main point that I want to address here is that in order for these equations to work, recall that this comes from the definition of a radian, right? So in order for these to work, theta has to be in radians, omega has to be in radians per second, and alpha has to be in radians per second squared. So in this context, the way these equations end up getting used is, if we were to focus on some point here, and I've taped my valve stem here in green tape to hopefully make it show up a little bit better. And so what we can do is we can use these relationships to compare, say, the angle that the wheel went through to how far this valve stem went. Alternatively, we could use these relations to compare the rate of rotation of the wheel to the linear speed of that piece of tape. Alternatively, we could use it to compare the angular acceleration of the wheel as a whole to the linear acceleration of a single piece of tape, right? So again, these equations, their job in life is to get us from the linear world to the angular world, right? And, in the previous segment, or a couple previous segments ago, we had the picture with the beetles on the record, right? And so if you imagine, a little beetle riding on that valve stem, that beetle is going somewhere, right? That beetle feels wind in his beetle hair, and he's having a big old time, right? So the beetle is going somewhere. He does have some translational motion. He can feel the wind in his hair. He's also rotating, right? And so these quantities would help us convert from the linear velocity of some point on that wheel, say the location of an animal like a beetle or any other small animal, and the overall rate of rotation of the entire wheel. Now we're getting to have a lot of accelerations here, aren't we? Right? We've got centripetal acceleration, tangential or linear acceleration, and now angular acceleration, right? And so, angular acceleration, right, we use alpha for that, and the units are radians per second squared, right? And something has angular acceleration if the rate of rotation is increasing, or changing, I should say, because slowing down will work too. So rate of rotation is changing. Right? Now let's compare that with, the acceleration we learned about before. And this can be speeding up, slowing down, or turning a corner, right? Now, this business right here, we call this the centripetal acceleration. Okay, so we call turning a corner the centripetal acceleration. You know, we could call these two the rate of change of speed, right? This is the only one, though, that refers us to a rate of rotation changing. The rate of rotation is changing, and that gives us an angular acceleration, right? And so this picture here can show us that for some particle, if the rate of rotation is increasing for some particle, then we could have all three kinds of acceleration, right? So in this case, v is increasing, which gives us an increasing tangential, gives us a tangential acceleration. It is turning a corner, which gives us a centripetal acceleration. And its total acceleration then is pointed like this. Now, since it has a tangential acceleration, it also has an angular acceleration, right? So we have to be a little bit careful about that. It's a little bit tricky.